This video is on the topic of gas pressure. The learning objectives are on your screen, so go ahead and pause the video and write those down in your notes. To begin the topic of gas pressure, it's useful to first discuss pressure in terms of something we might have heard of, atmospheric pressure. And atmospheric pressure is we define it as the force exerted by a column of air in the atmosphere. That force on 1 square inch of space. That's one way to think about atmospheric pressure. And the amount of force exerted on a given space actually turns out to be about 14.7 pounds as a weight of force on 1 square inch of space. And so that's equal to 1 atmosphere of pressure. So in general sense, and as you'll see in a second, we actually, I already mentioned units of atmospheres, and I've also mentioned pounds per square inch. Really there are a number of units of pressure, and the main thing to keep in mind is the general definition of pressure defined as capital P is going to be force over area. So pressure is directly proportional to force and inversely proportional to area. The pressure units I mentioned are right here. I'm going to quickly breeze through these. Definitely use this table use this table to help in your problem solving practice. So the Pascal is the SI unit, or the recommended IUPAC unit. It is the only one here you'll notice that's defined in terms of SI units of force and sort of length, so Newton per meter squared. So the kilopascal is just, the same prefix multiplier, kilo, so I'm not going to go into that. PSI, pounds per square inch, I already mentioned that. At sea level, which is about 1 atmosphere, it's about 14.7 pounds per square inch. This is a really useful relationship here between atmospheres. We have 1 atmosphere of pressure is the equivalent of 101,325 pascals, and that's equal to 760 torr. So one of the common ones that I remember definitely is that 1 atmosphere is equal to 760 torr. That one definitely is a very common conversion. We also have bar. This is specific to, not specific, but commonly used in meteorology. 1 bar is equal to exactly 100,000 pascals. A millibar is just, the prefix modifier, milli. Inches of mercury is one of my favorite ones just because it's literally the displacement of liquid mercury measured in inches. And that's typically resulting from devices that have been designed to measure pressure, barometers and manometers, and we'll talk about those in a little bit. 1 inch of mercury is equal to 3,386 pascals. The torr itself, I mentioned torr up above, that 1 atmosphere is equal to 760 torrs. This is just the torr defined as in terms of just 1 torr. It's equal to 1/760th atmospheres. I just find it easier to remember that 1 torr is equal to that 1 atmosphere is equal to 760 torr. Millimeters of mercury is quite similar to inches of mercury in that it's the displacement of liquid mercury. 1 millimeter of mercury is about 1 torr, so the other way to say that is that 760 millimeters of mercury is equal to 760 torr, and both of these are equal to 1 atmosphere. So interconverting these is pretty much dimensional analysis, so I'll leave it to you to practice that. We'll get practice in class. What I want to jump into is how to measure pressure. So this is an example of a barometer. This is one type of instrument used to measure pressure, and a barometer is typically used to measure atmospheric pressure and changes in atmospheric pressure. You can use a barometer that has liquid water in the bottom in this container that's open to atmosphere, but you can also use liquid mercury that's in the container that's open to atmosphere. The benefit of using liquid mercury, is that it's much more dense. It's a liquid with a much higher density than water. So that means that if there are kind of big changes in pressure, the vertical displacement up in the tube of the barometer won't be that high because it's such a dense liquid. And I'll give you an expression for that accounts for liquid density in a second. But you'll see that water, has much lower density. In order to measure pressure changes, we actually have to have much higher displacements of water in the tube. So for practicality reasons, mercury makes a lot of sense for measuring changes in pressure. We don't want to have to make this gigantic barometer tube in which just so that we can allow the water or some not very dense liquid to shoot up and have very big displacements. Okay, so it's strictly practicality purposes. Certainly not for safety reasons to use mercury, right? Okay, so the premise here is that there's this secondary container open to atmosphere, and we have this closed end tube that is vacuum sealed that's inverted. So what happens is there is some equilibrium that's maintained that's reached when atmospheric pressure is pushing down. But if atmospheric pressure increases and it pushes down on that liquid surface, then the displacement within this tube will go up, and it will push. If it's higher atmospheric pressure, it will push the mercury up into the tube, and we can measure that displacement in inches of mercury or millimeters of mercury, whatever we want. And also, if the pressure drops back down below atmospheric pressure, or there's just a decrease in atmospheric pressure, we would see that vertical displacement go back down in the barometer. The mathematical expression that I mentioned for a barometer is that we have the pressure that we can measure is going to be equal to this. This is supposed to be a capital P. Is equal to H times. This is not a P. This is the Greek letter rho. I did not really. It's kind of difficult to draw Greek letters sometimes. Maybe I'll draw it more like this to emphasize that it's not a standard P times G. H here is the height of the fluid. And we can also think about the height displacement of the fluid. Rho here, so when I'm saying rho, it's RHO, is a typical Greek letter used for density. And this is where the density of the liquid comes into play. And then G here is actually the acceleration due to gravity. But if we use a single liquid, then that means that the density is a constant. The acceleration due to gravity is a constant. So really the pressure is directly proportional then to the height of the liquid that we can measure in a barometer. But a barometer is useful for atmospheric pressure. What's more useful in a laboratory setting is to be able to actually measure the pressure of a sample, for example, not just the open atmosphere. So this is an example of a manometer. And a manometer actually it's not open to atmosphere. You have a sample reservoir that we can sort of, in a controlled manner, introduce to this either a closed tube system with a U-tube shape down here, an inverted tube filled with liquid mercury. There's also another design where we have an open atmosphere, open-ended tube where now we have to also account for the pressure of the atmosphere in our calculations. So the main premise here is that if we introduce to our manometer a sample of gas that has any really measurable, gases will have measurable pressure, but if it's a volatile liquid that has a substantial vapor pressure, what will happen is that when we open up this valve here, the pressure will force the liquid mercury down, right? There's a greater pressure in this side of the manometer, and that will cause this sort of vertical displacement on the other side of this inverted tube. Since this is closed to the atmosphere, it's a closed system, we don't have to account for the atmospheric pressure in our calculations. The pressure of the gas is going to be equal to the height times rho times, or height times density times the acceleration due to gravity. So essentially, that vertical displacement is directly proportional to the amount of pressure from our gas sample. And we'll look at one practice problem in a second that deals with that. In the open-ended cases, so both of these on the right are open-ended cases, but the situation over here is when the pressure of our sample is less than that of the atmospheric pressure, okay? And so what happens is, since the other end is not vacuum sealed, it's open to the atmosphere, then we also have to always account for the fact that there's atmospheric pressure pushing down on the open end of the tube. So if we open up this valve to our sample gas, and that sample gas is not pushing with 1 atmosphere of pressure, or 760 millimeters of mercury, or 760 torr, whatever unit you want to describe 1 atmosphere as, then that means that if it's less than 1 atmosphere, the atmospheric pressure will push down the liquid mercury and will actually measure a net negative displacement in the liquid height in our manometer. And you can imagine a case, it doesn't show it here, but imagine a case where the gas sample pressure is exactly equal to 1 atmosphere, then you would measure a net 0 displacement in the liquid height. Okay, that means that the sample pressure is equal to, or the gas pressure is equal to that of atmospheric pressure. Now, in the case where we have the gas sample, when opened to the atmosphere, actually is, or open to the manometer, is greater than 1 atmosphere of pressure, then that means that this will not only, it has to overcome the force of the atmospheric pressure, but also it'll push just a little bit beyond that. So if it was exactly 1 atmosphere, we would measure no displacement. If it's above 1 atmosphere, it will push the liquid mercury down over here, which causes a vertical displacement on the inverted side of the manometer. And then here you can see in these expressions for the first case that I described in the open-ended manometer, the gas pressure is actually equal to the atmospheric pressure. It has to account for that. And then in this case, it's if we measure that negative displacement in height, so it's minus height times density times acceleration due to gravity. So that means that this would indicate a system or a gas pressure less than that of atmospheric pressure. And in the other manometer case, where we have a gas sample with greater than atmospheric pressure, we have to say that the gas pressure is equal to 1 atmosphere because it overcame that 1 atmosphere, the atmospheric pressure, plus whatever that displacement height was. So let's take a quick look before I end the video, at 2 examples. The first one is going to be the closed-end situation, so we do not have to account for atmospheric pressure in our calculations. The question here that we want to answer is, what is the pressure in torr based off of this diagram that we can see here. So what we can do is, and again, this is liquid mercury. This is mercury. Okay, so to start, we can use our starting value that we're reading directly off that manometer, 26.4 centimeters of mercury height displacement. And essentially what we can do then is we can say that that is a unit of measure of pressure, centimeters of mercury, although it's not a common one. So we want to convert it to torr, which is more common. So what we can do is actually say, okay, well, if it's a centimeter of mercury, that's just the length unit. We can actually convert the length unit from 1 centimeter to 10 millimeters of mercury. It's that straightforward. And now that we're in millimeters of mercury, that is a common pressure unit. So now we can say, use a conversion factor here, 1 millimeter of mercury is equal to 1 torr. And so really this is 26.4 times 10, so it's 264 torr for our gas pressure there. Okay, and now in the open-end case, we have to consider the atmospheric pressure. And I guess I'll point out too that the benefit of the closed end, you notice that the gas pressure is 264 torr. Atmospheric pressure is 760 torr, so that's not greater than atmospheric pressure. So if this was the open-ended case, we wouldn't get a vertical displacement in the liquid mercury. It would actually go down because atmospheric pressure is greater. So speaking of open-ended cases, let's look at this case. Here we can make a prediction that this gas sample must have greater than 1 atmosphere pressure because look at this, it was a vertical displacement of liquid mercury on the other side. So that gas sample must have overcome the atmospheric pressure and then some. So let's do a calculation to see if that's the case. What I'm going to do here is essentially jot down, first let's see, what do we want to solve for? Let's solve for this pressure in atmospheres. Pressure in atmospheres. Is it greater than 1? So what I'm going to do is actually take this step by step and say that we have 13.7 centimeters of mercury, similar to before. I'm going to convert that into millimeters of mercury first. So this is 1 centimeter of mercury is equal to 10 millimeters of mercury. And I can jump, I can keep going from here, but I want to actually just pause to now talk about what we just calculated. This 137 milligrams of mercury is not the pressure of the gas sample. That's the additional vertical height gained just right here. But remember, this is open to the atmosphere. So this pressure, 137, is what was on top of atmospheric pressure. So really, the pressure of the gas is going to be equal to the pressure of the atmosphere plus whatever we just calculated, that vertical displacement, plus 137 millimeters of mercury. So what this equals is 760 millimeters of mercury for atmospheric pressure, which is approximating about 1 atmosphere, which is 760 millimeters of mercury, plus 137 millimeters mercury, and that will give us the pressure of the gas is actually 897 millimeters of mercury. Okay, so that's from the equation that I gave you above. So what is this in atmospheres? We take 897 millimeters of mercury, and we know that the conversion factor is 760 millimeters of mercury is equal to 1 atmosphere. 1 atmosphere. So what this gives us then is 1.18 atmospheres. We did predict, just based off of looking at how the displacement occurred in the manometer, that it's greater than 1 atmospheres, and we have confirmed that in this example problem.